A Fenwick tree, or binary index tree, is a data structure that keeps an array and supports two operations: prefix sum, given an index I, return the sum of elements from 1 to I, and point update, add a delta to the element at index I. We use one-based indexing, indices from 1 to n. In zero-based languages like Java, use an array of size n+1 and pass I+1 when you call query or update. The algorithm is unchanged. Both operations take logarithmic time and we use linear space. That beats a plain array, where updates are fast but query is slow, or a prefix array, where query is fast but update is slow. Fenwick trees are used for range sum queries with updates, inversion count, and order statistics. A Fenwick tree looks like a standard array on the outside. We use a one-indexed array from index 1 to n. In a normal array, every slot is an island. Index 3 only knows about the value at index 3, and index 4 only knows about index 4. For fast range sums, those isolated slots would need to share information instead. The Fenwick tree keeps a second row above the data array. Each slot in that row is responsible for a range that ends at its own index. At index 1, the range is just 1 to 1. At index 2, the range is 1 to 2. At index 3, the range is only 3 to 3. At index 4, the range grows to 1 through 4. When we line up the slots by range size, a tiered shape appears. Length 1 stays at the base, length 2 sits in the middle, and the largest ranges rise to the top. The dotted lines trace how larger ranges sit on top of smaller ones. All of this structure is still stored inside one flat array. There is a strict pattern here: every range length is a power of 2, 1, 2, 4, 8. Each range also extends backward and always ends at its index. Slots on the same tier never overlap. Index 2 owns 1 through 2, and index 6 owns 5 through 6, with a gap between them. A higher slot like index 4 can cover 1 through 4, so later we never double count. The flat array encodes its own tree layout in binary. When we write each index in binary, a clear pattern appears. On the base row, there are no trailing zeros, each string ends in 1. On the middle row, there is one trailing zero. On the top row, there are 2 or more trailing zeros. There is a precise rule for range size: the length equals the value of the lowest set bit. Index 6 is binary 0110. Its lowest set bit is 2, so it covers a range of length 2 ending at 6. Index 4 is binary 0100. Its lowest set bit is 4, so it covers a range of length 4 ending at 4. Because of this, any index x knows its exact boundaries instantly. For index 6, 6 minus the lowest set bit 2, plus 1, equals 5. The responsible range is 5 through 6. It looks backward by its own lowest set bit to find the start. By reading its binary pattern, every slot in a flat array can compute its range with no pointers. Every Fenwick step needs the lowest set bit of an index. Loops and conditionals are too slow, we need that bit in one machine step. For index 6, binary 0110, the target is the rightmost one, value 2. Plane shifting cannot peel it off without disturbing the rest. The fix is a trick built into binary arithmetic itself: isolate the bit instantly, with no scan. Computers store negative numbers with 2's complement. To build -6, flip every bit of 0110, you get 1001. Then add 1. The bits ripple into 1010, the binary form of -6. Now combine the original 6 with -6 using bitwise AND. Column by column, mismatches become 0. Only the lowest set bit column stays aligned, 1 and 1. Everything else wipes away, leaving 0010. The lowest set bit, value 2, in one fast step. The expression x and negative x is the fundamental engine behind the entire Fenwick tree. It extracts the lowest set bit instantly, the range size, and exactly how to steer during queries and updates. Now that we have our architecture, let's see it with a live dataset. When the array populates, each Fenwick slot computes its internal sum. Odd indices copy their baseline values straight up, 3, -1, 5, and -3. Index 2 stores 5. Index 6 stores 9. Index 4 rolls up to 10, the sum of the first 4 elements. Index 8 holds 24, the total across the whole array. These pre-computed blocks are ready, we can harvest them for any prefix sum. Our goal is the prefix sum through index 7. The brute force benchmark adds every value from 1 through 7, 3 plus 2 minus 1 plus 6 plus 5 plus 4 minus 3 equals 16. We initiate our query at index 7. Our engine reads the value inside node 7, which is -3, and adds it to our running total. To find out where to collect our next batch of data, we apply our bitwise formula. 7 and -7 equals 1. We subtract 1 from our position, leaping backward instantly to index 6. Now at index 6, we harvest its range value. Node 6 holds the pre-computed sum of elements 5 and 6, which is 9. We add this to our total. We calculate our next leap, 6 and -6 is 2. We subtract 2 from our position, bypassing index 5 entirely, and land smoothly on index 4. Finally, we reach index 4. Node 4 is a high-level power node holding the pre-calculated sum of the entire remaining prefix from elements 1 to 4. We harvest its value of 10, bringing our total to 16. Our bitwise calculation reveals our next index is 4 minus 4, which equals 0. Hitting 0 signals our exit gate. In just 3 clean steps instead of 7, our engine delivers the perfect prefix sum of 16. Now let's look at how the Fenwick tree handles updates. Suppose we modify the value at index 3 of our raw data, increasing it by 5. Because this is an overlapping tree structure, we cannot just change index 3 in isolation. We must march forward and climb upward, injecting this value shift into every single parent range that contains index 3. Our update begins exactly at index 3. Node 3 manages a range of size 1, meaning it is directly responsible for this slot. It absorbs our delta of 5, shifting its internal value from -1 to 4. To find our next target, we use our bitwise formula in reverse. Instead of subtracting, we add the lowest set bit. 3 plus 1 equals 4, climbing us directly to our first parent node. Now at index 4, our pulse encounters a major power node. Since index 4's range covers elements 1 through 4, it inherently owns a piece of index 3. It absorbs the 5-unit shift, updating its sum from 10 to 15. We calculate our next upward step, 4 plus 4 equals 8. The tracking line vaults forward, targeting our final global parent. We reach index 8, the absolute roof of our tree structure. Because index 8's range stretches all the way back to the beginning of the array, it must reflect the change we made down at the bottom. It absorbs the final wave of our update. The engine checks for the next parent, 8 plus 8 is 16. Since 16 exceeds our maximum array size, the update loop cleanly terminates. In just 3 vertical hops, every affected range in our infrastructure has been perfectly synchronized. Let n be the number of elements. Prefix sum query and point update each touch at most log n tree cells, O of log n time. Building the tree from the data costs O of n log n, space is O of n for the tree array T. Here is the pseudocode for the 3 routines we used: low bit, prefix sum query, and point update. Feel free to code along in your favorite language. Low bit of I is the lowest set bit, I and -I, the same formula from the bitwise section. Query of I returns the prefix sum of a from 1 to I, add t at I, subtract low bit from I, and repeat until I is 0, the same downward walk as in our query example. Update of I with delta propagates the change up the tree, add delta to t at I, add low bit to I, and repeat while I is at most n, the upward walk from our update example.